Okay, good morning. I'm Silvio Savarese. I'm an assistant professor in computer science in Stanford, and I direct the computational vision and geometry group. So my talk is about what makes an environment smart. So sensing is the future, and sensor will be everywhere, and it will be ubiquitous. It will be in our cities, it will be in our cars, it will be even in our shoes. And they will also be intimately connected to us, to the point that we have to really start getting used to it, and as this comic shows. So almost everything is a sensor, and a plant, the antennas of a snail, our nose, eyes, fingers, and tongue. And in the recent year, we have seen that an explosion of new artificial sensors, for instance, for measuring temperature, pressure, humidity, weight, heartbeats, and so on. But sensing is not the hard problem here. Intelligent understanding of the sensing data is the challenge. And this is a critical observation. For instance, adding intelligence to sensor would transform our houses. A typical example is a smart house, which is supposed to be sensitive to the presence of users. Sensor would supply data to the system in the form of images, sounds, smells, and the systems will exhibit intelligent behavior. For instance, it will be able to recognize each individual in the household and adapt its behavior according to their needs. Adding intelligence to sensor would transform our cities. The environment can provide critical feedback to autonomous vehicles, pedestrians, and drivers. Adding intelligence to sensors would transform the way we manage disasters. Here, the smart environment is populated by distributed agents, robots, drones, vehicles, which can explore a site for real-time assessment of disaster risks. So, what makes an environment smart? First, the ability to sense the world, then to associate sensory signals to semantics and language, and then to understand human instructions, if any, and finally to act appropriately. And in this talk, I will be interested mostly in focusing on these first two items. So what are the key players in these scenarios? So the sensors themselves, so the multimodal sensor, vision, sound, touch. And since I work in computer vision, I'm interested in using sensors such as RGB cameras, depth cameras, stereo systems. Another important piece of the puzzle is the environment. That is the objects we want to recognize, the people we want to detect, and the space we want to understand. And third, the semantics, the story we want to make out of these observations. The prior knowledge we know about the world, the context we learn from related observations, and the intelligent action we want to make as a consequence. So my students and I have been interested in exploring ways for connecting those components, and I find that this is really exciting. So we've been working on methods that go beyond just 2D image classifications, but can estimate the physical properties of the world. For instance, not just detecting bounding boxes of objects from images, but also discovering their 3D properties, such as pose and geometry. Not just online tracking as 2D template matching problems, as shown on top here, but also as a tracking the 3D aspects of objects and learning its appearance along the way. And there's going to be a poster this afternoon talking about this in more details. Not just to the object segmentations from a number of views of the same environment, but semantic reconstructions. So being able to localize the objects in 3D, such as those cars, those pedestrians, as well as certain elements of the surface of the road, the building facades, as well as the cameras. Not just to the 2D multi-tracking, but also 3D localization of targets and 3D navigation. Finally, not just recognition, but also modeling, not just action recognition, but also modeling human interaction in 3D and predict complex behavior, such as being able to tell that these two groups of people are talking, but also separating them into groups and telling that these two groups are not actually interacting to each other. So let me spend the second half of this talk with an example of a smart environment, which I find very exciting and interesting. This is relevant to information management and construction business. And my group has been working in this framework for the past few years. So in construction business, a smart sensory system can be used for analyzing the status of a construction site and also enable the automatic coordination of the construction progress. So let me give a bit of context here and why this is an interesting application area for vision and robotics. So what we see here is the San Francisco-Oakland Bay Bridge, the largest self-anchored suspension bridge in the world, and one of the largest public work in California last decades. And it was completed last year in September 2013 to replace its predecessor, which collapsed because of an earthquake. So its final cost was as high as 6.4 billion. And we also have heard that the opening of such impressive piece of work followed years of disputes prompted by designs, struggles, and financial issues. And it came as at most at 5 times the estimated original cost. And it was 6 years behind schedule. So this is just a striking example of an dynamic condition in construction business. The size of the US construction industry today is 900 billion US dollars every year, and the statistic shows that the loss due inefficiency in productivity amounts to about 10%, which is 90 billion per year. And this is not a surprise. Nowadays, the progress of construction projects are monitored through a complicated process which involves the collection of data from field engineers, the analysis of such data in weekly coordination meetings. And this process is very time-consuming, it's not systematic, and it's prone to many errors. So it has been shown that improvement of as little as 1% can lead to huge savings, up to 900 million. And there's really an opportunity to modernize an age-old process in a profound way. So my students and I have proposed a novel approach to these problems, and we have thought of a construction site as a smart environment. So here, images and other sensory inputs are acquired from the site, and they're processed through computer vision technology. So good news is that those images can be easily captured from surveillance cameras, from cameras mounted on workers, from drones, from autonomous segways. And these are some examples of the images that we can acquire. Also, we can input other sensing modalities, such as barcodes and radio frequency ID tags. So, and then we can do, with all this data, we can do 2 things at the same time. So we have shown that our framework allows to produce an accurate metric reconstruction of the geometry of the environment, as well as the identification of the important semantic phenomena, such as pillars, scaffolder, walls, and so on. And by comparing the semantic reconstruction of the S-build model, as you see on the top left, with the S-plan model, at any given day, and this S-plan model comes from the prior knowledge that we have about this environment, we show that it can automatically predict elements that are constructed on schedule, ahead of schedule, or behind schedule. And these are shown with different barcodes here. So red behind schedule, green on schedule, and dark green ahead of schedule. And therefore, it's possible to use our framework to enable automatic coordination of construction progress element by element and day by day. So in summary, our framework allows to do better tools for visualizations. It enables automatic communications of performance deviations, and also it reduces the delivery time. And critically, for future work, we are hoping we can use this also for safety management and to identify potential areas which are unsafe for workers and for engineers. And this had a large impact to the community, to the civil engineering community, and so we got a number of awards for that, and to acknowledge the importance of this line of work in their field. And with this, I would like to thank you for your attention.
I have sound.
Yes. Right, so other application we are looking for beyond civil engineering, also for the smart houses, so for smart environment, in particular for actually smart vehicles, so the ability to provide smart information to the drivers when they drive, so not just as a way to fully replace not just to design an automatic autonomous system, but to actually to provide useful information for drivers and to assist during their driving experience.